Hello! In this talk, I will be presenting integral formulations of volumetric transmittance by Iliyan Georgiev, myself, Zachary Misso, Toshiya Havhisuka, Derek Nowrouzezahrai, Jaroslav Jrivanek, and Wojciech Jarosz. This presentation is about rendering participating media which can take the form of clouds, fire, liquids, or even stained glass. These visuals are very common, so it is imperative we have methods to render them realistically and efficiently. So, how exactly do you go about rendering volumetrics? Well, participating media is physically comprised of hundreds of thousands of small particles which can interact with incident light. However, instead of simulating these particles individually, we normally represent volumes as density. The behavior of light inside a medium then becomes the result of a random process with two key operations. The first operation involves determining the points within the medium where specific light paths will scatter, while the second operation involves estimating the attenuation of light along some path segment. This quantity is known as the transmittance. Our work only considers the latter problem of estimating transmittance between 2 points, A and B, where it is defined as the proportion of light reaching A from B. Most of you may be familiar with the exponential form of transmittance, which states that your radiance will diminish exponentially according to the optical depth of your medium. The optical depth, tau, is further defined as the integral over the extinction of your medium, which we call mu. The extinction is the combined attenuation from both scattering and absorption along some stretch of the medium. You can think of this quantity as the density of your medium at any point x. Therefore, the exponential form of transmittance basically states that the more dense your medium, the more collisions there will be between photons and particles, thus the less radiance will make it through. Unfortunately, in the general case, analytically computing the optical depth is prohibitively expensive. So, how does previous work go about estimating this quantity? The first proposed unbiased transmittance estimator was delta tracking, and it works by first homogenizing the density in the medium by adding fictitious or null particles. The estimator then begins a random walk by sampling an exponential free flight distance starting at A. After it takes this step, it performs a lookup into the medium as indicated by the green circle. During this lookup, it samples the null extinction and real extinction at this location. The proportion of real and null particles can then be used as a Russian roulette continuation probability, dictating whether or not a real particle or a null particle is hit. If the estimator hits a null particle, it samples another free flight step, and the entire process repeats. If it samples a real particle, it terminates and returns an estimate of 0. If a real particle is never hit and the estimator eventually reaches B, then it returns an estimate of 1. This estimator is simple to implement and to understand since it returns either 0 or 1 depending on if a real collision occurs. And while you can prove that this process is unbiased, the proof is very involved since it is not just a simple application of Monte Carlo. So why not attempt to apply Monte Carlo to estimate transmittance directly? The optical depth is defined as an integral over the extinction, so let's naively apply Monte Carlo to estimate it by looking up the extinction at a few locations in the medium and dividing by the probability density of choosing said points. While this Monte Carlo estimator provides an unbiased estimate for the optical depth, unfortunately, your estimate for transmittance will be biased. This is because the exponential is a nonlinear operator, so Monte Carlo cannot be used directly. This is due to the exponential representation for transmittance not being purely an integral formulation. It has an integral contained in it within the definition for the optical depth. But what we need is a definition for transmittance which is purely an integral with no nonlinear operator being applied to it. This is desirable because it is easy to derive unbiased estimators from such a formulation, since when you just apply Monte Carlo to it, you have an unbiased estimator as a result. This is what we sought out to do, and we ended up deriving 3 such integral formulations. While doing so, we also discovered parallels between our formulations and the various formulations for the rendering equation, which allowed us to explore well-known Monte Carlo design decisions in rendering, such as MIS or bidirectional methods, within the context of transmittance estimation. So, let's derive our first integral formulation. Starting from the differential form of the reduced radiative transfer equation, which basically states as you move along some infinitesimal beam, your radiance diminishes according to your extinction. From this, it only takes a couple of easy steps, which involves integrating both sides and moving terms around to reach an equation for transmittance which has the form that we want. This is, in fact, our first derived integral formulation for transmittance, and it was accomplished in a few easy steps, which are even simpler than how its exponential form was derived. Let's look at this formulation in more detail. You can see that it has an integral spanning from a to b, and within this integral, you have a recursive call. If you compare this formulation to the exponential form for transmittance, you can see we have transformed transmittance into something that does not just contain a one-dimensional integral, but is instead an infinitely nested integral. Now, how do we go about estimating this? By simply replacing the integral with a one-sample Monte Carlo estimator. Unlike previous work, this estimator allows for choosing any sampling routine as long as it has a valid PDF. But for simplicity, let's say we sample all our free flight distances with exponential distance sampling. So first, start at A and calculate the additive term, which for this dummy formulation is 1. Then you sample a free flight distance according to your PDF and march to that location. At this point, you evaluate the extinction by looking up into your medium, as indicated by the green circle, and finally you recurse and repeat the process until naturally your estimator reaches the end of the segment. Interestingly, delta tracking follows a similar process to this dummy estimator we have just visualized. In fact, the delta tracking and later formulated ratio tracking estimators can be derived directly from our first integral formulation for transmittance. Turns out, they just utilize different Monte Carlo design decisions. Remember that delta tracking introduces null scattering to homogenize the medium. We show in the paper that this is actually a form of control variance, which is another Monte Carlo design decision. To avoid complexifying the equations, we will just mention now that all estimators are derived from our integral formulations after applying control variance to them. But we will not show those in this talk. What is also very interesting is if you compare the process of our visualized estimator and unidirectional path tracing, it turns out that they are also very similar. The major difference being the green circles in the transmittance case are extinction lookups, while they are BRDF evaluations in the rendering case. If you look at the equation for our first integral formulation, it seems very reminiscent to the rendering equation. The only major difference between the two formulations is that while the integration bounds of the rendering equation remain constant, the integration bounds for the transmittance formulation change. Due to this difference, the transmittance integral is considered a Volterra integral, while the rendering equation is a Fredholm integral. Thus, we have dubbed our first formulation the Volterra integral formulation. Given the Fredholm representation of the rendering equation, we know that there are better performing integrators than just purely unidirectional path tracing, one of which is unidirectional path tracing with next event estimation. Turns out, within the context of transmittance estimation, next event estimation is also a design decision within our Volterra formulation, which is how the next flight estimator from the previous work is derived from the Volterra. So, to summarize what we have done so far, we have derived our first integral formulation for transmittance, allowing for unbiased estimators to be derived simply by applying Monte Carlo to an integral. We have shown, through analogies, that all previous unbiased transmittance estimators can be derived directly from this first formulation for transmittance just by choosing different design decisions. And we have introduced parallels between our integral formulation for transmittance and the integral formulation we know as the rendering equation. Now that we know there is an analogy between transmittance and the rendering equation, and we know we can represent the rendering equation in different forms, turns out those different forms have analogous formulations within the context of transmittance. First up, there's the Neumann series formulation of the rendering equation, which separates the integral of the original rendering equation into a summation over individual path lengths of length k. The Neumann series representation is analogous to our power series integral formulation for transmittance, which is derived by expanding out the exponential form for transmittance into its power series equivalent. Once you represent transmittance as the sum over all path lengths, there arises two classifications of estimators which can be derived from this formulation. A prefix sum estimator, which evaluates all paths up to length k and divides by the probability of reaching length k, akin to how unidirectional path tracing with next event estimation sums up different path lengths through shadow connections. And a single term estimator, which evaluates one path of length k and divides by the probability of choosing that exact path, which is loosely similar to naive unidirectional path tracing, where you terminate after hitting your first emissive object. These graphs are both represented as Poisson distributions because, once control variates are applied, this is reminiscent to the shape that the contribution of any power series estimator takes. However, for those gritty details, we point the interested reader or listener to our paper. In addition to the Neumann series, there is the well-loved path integral formulation for light transport. And similarly to how it is derived, you can merge all path lengths into the same space in the context of transmittance estimation to reach our hypercube formulation of transmittance. Now that we have an analogous path integral formulation for transmittance estimation, we can utilize bidirectional MIS methods from rendering to derive novel transmittance estimators, where instead of sampling subpaths from the camera and light sources, you sample paths from A to B and B to A using exponential distance sampling, then MIS all possible paths. Connecting two non-overlapping paths becomes just an exponential evaluation for the transmittance case. In summary, we have introduced three integral formulations for transmittance, each allowing for novel estimators to be derived by just applying Monte Carlo: Volterra, power series, and the hypercube integral formulations. While we do not have enough time to talk at length about all estimators in detail, we will briefly summarize them here. We have shown that all previous work can be derived directly as Monte Carlo estimators of the Volterra formulation, and have introduced a bidirectional estimator akin to bidirectional path tracing. In our paper, we introduce a unidirectional MIS estimator, which multiple importance samples between only ratio and next flight. We also redefined ratio and next flight within the power series formulation, which differ mainly from their Volterra counterparts by how they utilize their random numbers. Power series cumulative is a prefix sum estimator whose Russian roulette probability is based off of the cumulative weight of the contribution of the estimator, and power series CMF is a prefix sum estimator based off of the power series cumulative estimator, except it chooses to ignore Russian roulette until a majority of the expected CMF of the contribution has been accumulated. In essence, these two estimators trade higher cost for lower variance, except the latter estimator will strategically terminate earlier or later in certain situations to improve variance. All of these estimators have been enabled to be derived by the flexibility of our formulations and truly only differ within their respective formulations by what design decisions they choose to use. Now, how do these estimators compare? Well, before we delve into that, we need to define one last design decision, and that is defining the use of an upper control, or what previous work referred to as a majorant, which is used when control variates are applied. Basically, if you have a tight upper control, meaning the fictitious part of your medium is relatively small, your estimators will evaluate fewer extinction calls. And if you have a loose upper control, meaning the fictitious part of your medium is large, then your estimators will evaluate more extinction calls. While we explain this design decision in more detail with a more thorough performance analysis in the paper, for the scope of this talk, just make note that different estimators perform differently depending on this parameter, and that this parameter is linearly proportional to the time it takes to render an image. So now, we will go over its edge cases. First, let's look at the case where we have a relatively tight upper control using this homogeneous medium. For this, in all future scenes, we utilize a modified path tracer to evaluate all branches on reflective and refractive boundaries and only use fully absorptive mediums with no scattering to avoid noise from all sources other than transmittance estimation. We ran these estimators until an equal number of extinction lookups had been reached. For this scene, we compare the best two estimators from previous work, ratio and next flight, against our best novel estimator for this scene, power series CMF, which is in green. Our estimator performs near perfectly because its trade-off of higher cost for lower variance works extremely well when you have extinction functions with low to no variance. Now that we have looked at tight upper controls, let's consider loose upper controls, where we set the upper control to 5 times the max density in this medium. Practically speaking, loose upper controls are utilized when you cannot accurately calculate the bounds, or it is too costly to calculate the bounds on the medium, which is modified by some procedural function. For this case, we again compare the best two estimators from previous work, using equal lookup renders, against our best novel estimator for this scene, which is in green. As you can see, ratio tracking and our estimator perform equally well for this case. But we do need to note that as you increase the upper control of your medium, you would expect our estimator, the power series CMF estimator, to become too costly. Instead of dealing with inaccurate or large controls, which take a large amount of time to render, why not have just a non-bounding upper control which can render out more samples in a fraction of the time? Well, the problem is, the pseudo-physical interpretation of the upper control from previous work caused the variance of their estimators to be extremely susceptible to non-bounding controls. For this scene, we compare ratio tracking against our best novel estimator when applying non-bounding controls. Our power series cumulative estimator is the one we use, which is in green. We render both estimators when the upper control equals the max density in the medium on the top row and half the max density in the medium along the bottom row until an equal number of medium lookups had been made. While ratio tracking's RMSE starts to explode once you encounter non-bounding controls, the flexibility of our formulations enable us to implement more robust estimators, where, for this case, the RMSE of our estimator only increases by a minute amount. Lastly, it would be interesting to see how the various formulations perform when utilizing stratification. For this scene, we compare the Volterra formulation and power series formulation for equal pixel samples, where we utilize independent sampling for the top row and latent hypercube sampling in the bottom. We stratify across all path segments. For independent sampling, the Volterra and power series formulation for ratio tracking are equivalent. However, when you reformulate ratio within the power series formulation, due to how it uses its first random number to instead sample its path length k directly, it performs better with stratification. Turns out, all estimators derived from the power series formulation benefit significantly more from stratification than any other formulation. However, for brevity, we point the interested listener to our paper and supplemental for more details. So, which estimator is the best one? Unfortunately, there is no one-size-fits-all estimator yet. Ratio tracking is still the best choice for extremely sparse media or media with naturally loose upper controls. Our power series cumulative estimator is the best when supporting non-bounding controls, and our power series CMF estimator is typically the best for all other cases. Despite not having discovered the best estimator, we have introduced the first integral formulation of volumetric transmittance, and in doing so, we have allowed for the use of various Monte Carlo design decisions, allowing for flexibility in designing transmittance estimators. This flexibility has allowed us to reformulate previous transmittance estimators within our own framework through analogies to the rendering equation. We have also introduced 4 new novel transmittance estimators. However, our formulation gives us and other rendering experts the means to develop many more. In the future, we hope to formulate our theory to support non-exponential media. Also, we would like to look into applying our formulations to sampling scattering events instead of just transmittance estimation. And lastly, we would like to look into more MIS estimators since we did not get to thoroughly explore that space. Thank you very much for listening, and for more details you can visit our website to read the paper, view our supplemental, and see more of our results up close. If you are interested, we also have some example code of our various transmittance estimators on GitHub.